Hello, Longhorns. Today we're going to take a look at the work kinetic energy theorem. We're going to combine two of the concepts that we have been looking at since we finally made it to lesson number 8. Still in chapter 5, pages 160 through 164. Don't forget, a good tip is to always have your PowerPoint in front of you. So either have a second screen or even a printout. The other thing you may want to do before viewing the videos is go ahead and take a look at the first page or two in the textbook as well. Let's get started. One concept we are pretty clear on, that kinetic energy is energy of motion. So whenever you're asked to give that simple definition, keep in mind, if the object is not moving, it does not possess kinetic energy. We represent kinetic energy with the capital K and E. Now, there's also an equation that goes with kinetic energy, our energy of motion. Your kinetic energy is equal to 1/2 times mv squared. By now, we know that the letter M stands for mass, which is measured in, gotta have your kilograms, and velocity as well, which is meters per second. The most common thing for students to forget is either the 1/2 that actually accompanies this entire part of the equation, or the square that's on your velocity. And we'll take a look at that in a few different ways. Here's a sample problem. What is the speed of a 0.145 kilogram baseball if its kinetic energy is 109 joules? We've seen this unit before, so don't forget that both work and energy are both measured in joules. We're going to use the guess method to lay this problem out for you. So, in the problem, they provided us with a mass of 0.145 kilograms. They also told you that your baseball had a kinetic energy, Ke, of 109 joules. You were asked at this point to find your unknown, which is speed, which we know they're referring to velocity. And our equation that we just came across is 1/2 mv squared equals your kinetic energy. You normally I have it on this side, but kinetic energy is equal to 1/2 mv squared. Now, for your substitution step, we have to ask ourselves, is there anything that we need to convert? In this example, our mass is in kilograms. Kinetic energy is already in joules, so we are good to go. With no substitutions, let's prepare to solve. Now, there are two different ways to kind of tackle this one. If you take a look in the textbook, you will notice that I believe on page, probably 2 or 3 pages in, they have actually gone ahead and rearranged the equation for you. So it starts out as Ke equals 1/2 mv squared. We're going to learn that we need to remove the square, and we've used the square root before to do that. Let's rearrange this equation, and it's going to become V equals the square root of 2 times Ke divided by M. All right? Now, this is provided for you. It will normally be worked for you as well. Let's go ahead and plug in our numbers and see what we have. V equals, remember for kinetic energy, we had 109 joules, and our mass was 0.145. Grab your calculator. We'll first multiply our two numbers on top. So 2 times 109 will give you 218. And you still have your 0.145 on the bottom. If you go ahead and divide your number, we will be left with taking the square root of 1,503.4. My final velocity is 38.77 meters per second. Now, one common area where students struggle is when they're actually trying to put in the number and make sure they have the square root. There's a big difference between taking the square, which is similar to 5 times 5 if you were taking the square root of 5, compared to taking the square root of 25 to get 5. So make sure that what you're putting in your calculator also agrees with what is on your paper. Your given information was here. Our unknown was velocity. This was the original equation that we were given. You would normally take the square root on both sides to remove your square. You would also flip your fraction in order to move the 2 to the top, and that 1 is imaginarily still at the bottom. We knew we wanted to solve for velocity by itself, so we had to be sure to multiply, divide, and then follow our steps all the way through. The biggest thing about kinetic energy is making sure you label your parts or moving parts properly. Now, since we have kinetic energy and we've learned that there are several different types of energy, we won't hesitate that we're going to see other types of energy pop up in your equations as well. So if they describe something that's moving and then it's generating heat, we know that energy cannot be created or destroyed. So it's simply changing form. It's going from one form of energy to another. And heat is one of those very common forms that we're going to run into. Now, when we put it all together, here's another thing that we're going to notice as well. Work equals a change in kinetic energy. We've used capital W for work, the delta sign, or that triangle that we see really often, which means a change in, and then KE stands for your kinetic energy. And remember, work and energy are both measured in joules. When we put this all together, this change in energy is known as your work energy theorem. This is the way it's written in your textbook. So the net work that is done is equal to a change in kinetic energy. We're simply going to take our two parts and put those together. What I want you to do is we're going to set up the first practice problem from the textbook. I'll give you the G, the U, and the E, and we'll make sure that no substitutions are needed. I want you guys to go the next step and go ahead and attempt to work out that particular problem. And if you get stuck, let me know. So, we have a student wearing frictionless inline skates on a horizontal surface is pushed by a friend with a constant force of 45 newtons. How far must the student be pushed, starting from rest, so that her final kinetic energy is 352 joules? We just went from a simple work equals force times distance to kinetic energy equals 1/2 mv squared. And now we have a combination of things that are coming together. But let's think about it. We're talking about a force being applied to an object. What equation do you remember that was force equals mass times acceleration? Which of Newton's laws was that? Second law is exactly right. And if you keep that in the back of your mind, it'll be helpful for you in a little bit. Let's show our given, and we'll set this one up for you. A student wearing frictionless inline skates on a horizontal surface is pushed by a friend with a constant force of 45 newtons. So our first piece of given information will be force. How far must the student be pushed starting from rest? So the initial velocity was 0 meters per second. So that her final kinetic energy is 352 joules. So that's my KE equals 352 joules. They wanted to know how far, so we're looking for distance. And we're coming down to our equation. We want to know how much net force for your change in kinetic energy. Now, here's another way to look at this problem. You guys know that work is equal to what? Force times distance. So let's expand this out. What if I took my equation? We're going to use our substitution step for this. And instead of putting W, we put in force times distance. We also know the kinetic energy is equal to 1/2 mv squared. Now, let's look. We have force. Distance is your unknown. We don't quite have a mass, but we know that our velocity is 0, right? So, I want you to take a second, see what you come up with on this problem, and if you happen to get stuck, send me an email and let me know. Before you go, any questions can always be emailed to me, or you can plug them into Remind, and we can have quite a few people take a look. Here's another video that you may enjoy that gives you a little bit more information on the work kinetic energy theorem. We'll tackle these larger problems in class as well, and you have a few to work for your resource and for homework. I'll see you guys in class.